This is Algebra Lesson 9.1, Geometric Sequences. So a geometric sequence is a list of numbers that changes using multiplication. So the easiest example is doubling, which is kind of close to example A, 2, 4, 8, 16, 32, 64, 128, and so on. I'm doubling those numbers every time. I'm multiplying by 2 every time. We talked about recursive rules in an earlier chapter when we had our start and our change. So we're going to kind of use that language again this chapter. Start is obviously where it starts, and change would be how we get the next number in the list of numbers. Since we are focusing on geometric sequences, these will always be multiplying by some number, and we call that number the ratio. The easiest way to obtain the ratio is to take the second number and divide it by the first number, or any two consecutive numbers in that list of numbers. Example A says, consider the sequence 4, 8, 16, 32, and so on. Write the recursive rule. The recursive rule, I said, needs two things: where it starts and how it changes. So the start and the change. This sequence starts at 4. To get the next number, I am multiplying by 2. And if that wasn't super obvious, if you take 8 divided by 4, it tells you what it's multiplying by. To me, doubling 4 to 8, that should be really obvious, but maybe you'll have something less obvious, like how do you get from 72 to 68? How do I multiply to get from there to there? Take the second number, divide it by the first number, and that'll tell you how to multiply to get there. So my change here is that I'm multiplying by 2. To find the next three terms, I'm going to take that 32 and times it by 2. I'm going to take that 64 and I'm going to multiply it by 2. I'm going to take that 128 and I'm going to multiply it by 2. Those ones, to me, I remember pretty well because of size capacities, but you can always go number times 2, and then if you have a recursive setup, times 2, enter, 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 without even having to retype the times 2, it'll keep giving you the next, and the next, and the next, and the next answer. We did something very similar when we talked about our arithmetic sequences before our linear algebra chapter. So if I wanted to keep going to the 10th answer, I got this kind of on my screen already. I have answer 1, answer 2, answer 3, answer 4, answer 5, answer 6, answer 7. So if this is answer 7, answer 8, answer 9, and one more, answer 10 would be 2048. Imagine that a bug population has invaded your classroom. Every week, new bugs hatch, increasing the population. One day, you notice 16 bugs. 1 week later, there are 24 bugs. 2 weeks later, there are 36. 3 weeks later, there are 54. Record the total number of bugs at the end of each week for the 3 weeks in the table at right. So I got 16 already on there. I'm going to put 24 on there. I'm going to put 36 on there. I'm going to put 54 on there. Model the population growth by writing a recursive rule that shows the growing number of bugs. So we're going to use this idea that to calculate the ratio, we're going to take the second value divided by the first value. And it doesn't necessarily have to be the second divided by the first. It can be any two consecutive numbers. So 24 divided by 16, or 36 divided by 24, or 54 divided by 36, and so on. And I'm going to show you what I mean. So if I chose to go 24 divided by 16, I calculate a ratio of 1.5. If I go 36 divided by 24, I calculate a ratio of 1.5. As long as I'm taking any two numbers next to each other, dividing the later number by the earlier number, I get the same ratio. It's multiplying by 1.5 every single week. So my recursive rule needs two things. Where do I start and how do I change? This example started with 16 bugs as soon as I took notice, and the way that it changes is we are multiplying by 1.5. And I'm going to write this up here just so we know how we got that 1.5. 24 divided by 16 was 1.5. So I can keep going now. If I take my 54 and I multiply by 1.5, that tells me I will have 81 next week. And I'm going to multiply by 1.5 again, and I'm going to take this value, but I'm going to round it to 122. Hopefully there's no half bugs crawling around. And we're going to round this one to 182. And we'll round this one to 273. And our 8th week is going to give us 410 bugs crawling around the classroom. What is the bug population after 20 weeks? Well, I'm already on answer 8, so I can go answer 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. If you don't have a calculator that lets you do these recursively, grab one of mine because it's going to be a quick saver for you. So we're at 53,204. The last example says a half-life is the amount of time that it takes an element to decompose to half its current state. The half-life of carbon is 5,730 years. If Karen has a 30-gram sample of carbon, how much will be left after 6 half-lives? So I'm going to write a recursive rule to help me figure this out. How much do we start with, and how are we changing? In this instance, we are starting with 30 grams. And how are we changing? Well, that is half of its current state. So we are multiplying by 0.5 to get half of the original. So if the question is how much after 6, we're trying to find the 6th term in this sequence. If we start with 30, and then we take half of that, after 1 half-life, there is 15. After 2, after 3, 4, 5, and 6 half-lives, we'll have about half a gram of carbon. So we have 0.46875 grams after 6 half-lives. That is it for the notes. Good luck on the exercises, and please let me know if you have any questions.